Imaginary numbers. When my math teacher first introduced me to these things, I immediately just shut off. I mean, imaginary numbers? Why would I care about something that isn't real? Something that's just imaginary? Well, it's a misnomer. Imaginary numbers are actually very real, and let me show that to you. Originally, we only conceptualized numbers in one direction, positive. And this makes sense. I mean, you count to 5 on your fingers, 5 on the number line. But positive numbers alone can't solve all mathematical questions, of course. For example, how could you model things like debt or velocity with only positive numbers? Thus, the idea of negative numbers came about. But it wasn't initially well received. Many cultures, like the ancient Greeks, didn't believe in them, thinking they were an abomination. I mean, it's not completely unreasonable, though. How could you have less than nothing? For example, let's take the equation x equals 4 minus 5. If we have 4 coffee cups, let's say, and then we take away 5 coffee cups, our result is that we have less than 0 cups. How is that physically possible? But we eventually came to intuit that negatives are just opposites of positives. You can't really physically model having negative coffee cups, but we can look past that to solve math problems. We can apply this creative thinking to imaginary numbers. Now let's take a second to think about squares. Take the equation x squared equals 16. That means that some number x times itself equals 16. X can be positive 4 or negative 4 since the negatives reverse each other. But the main point is that we need to get to a number with two multiplications of the same number. But as soon as we do x squared equals negative 16, we don't really know what to do with conventional mathematics. It's easy to say that we just don't have a solution to this problem, but wait, we can't do that. A while ago, Carl Friedrich Gauss, a German mathematician, proved that any polynomial with a degree n that's greater than 1 has to have one root. It's called the fundamental theorem of algebra, so that implies that, it has to be a little important. And if we look back at our equation, it is a polynomial, and the degree is bigger than 1, so it doesn't really get an exception. Instead, we have to work through the problem. To solve this, let's look at a number line. For the problem x squared equals 16, if x is positive, we start on the right and just go a little further to the right. If x is negative, we start on the left, and because we multiply by a negative number, we get the opposite value on the right, because positive and negative numbers are opposites of each other. But for x squared equals negative 16, we start on the right, and we have to get to the left in just 2 steps. The backwards and forwards logic of negative numbers doesn't really work anymore, so we have to open up a new dimension, the imaginary plane. Instead of opposites in the imaginary plane, we have to rotate to get back to the left. So if we think of negatives and positives as related to each other by opposites, imaginaries are related to each other by rotation. This is where we can define I. I can be defined as I squared equals negative 1, the number where multiplied by itself is negative, or just I equals square root of negative 1 if you want to simplify. This opens up a new dimension, moving our simple number line into a more complex space. So our answer to the previous question, x squared equals negative 16, it's 4i. Using this creative mathematical thinking has allowed us to progress in many fields. Imaginary numbers are now used to describe wave motion of particles in quantum mechanics, since real numbers don't have the depth to do so, describe impedance in alternating circuits, which is widely used in electrical engineering, and such. The main takeaway about the story of imaginary numbers is that math isn't just a set of rules to blindly follow. It's a framework to further our understanding of the universe.